So in today's lab, we're actually going to get Alka-Seltzer. I did a demonstration, watch that demonstration, and we want to figure out the amount of sodium bicarbonate in Alka-Seltzer. So if you have Alka-Seltzer, Alka-Seltzer consists of, like in this case, it has um, sodium bicarbonate, that's an antacid, it'll have some aspirin in there, etc. And we want to figure out the percent of sodium bicarbonate in there. So again, sodium bicarbonate is just baking soda. So a couple of things. The way we're going to do this, we're going to use the ideal gas law today. So we're going to figure out how much carbon dioxide gas gets produced. And then from that, we can figure out the amount of sodium bicarbonate by stoichiometry. So stoichiometry doesn't go away for us. So a couple of things, some of the raw data that you're going to need to do this. You need atmospheric pressure since we're dealing with a gas. So in this case, that's 767.5 millimeters of mercury. So that varies from day to day, but it's around that. Uh, Temperature, so room temperature, so everything's done at room temperature. So that's going to be 22 degrees Celsius. Whenever you deal with ideal gas laws or any of the gas laws, the main thing is convert it to Kelvin. So always convert everything to Kelvin. So I added 273 to do that. And then right here is water vapor pressure. So if you look at that video, we have a little bit of water vapor pressure that builds up during the course of the reaction. Mostly we have pressure due to carbon dioxide gas, but there's a little bit of water vapor pressure. This value you look up, so it depends on the temperature. So at 22 degrees Celsius, vapor pressure is 19.8. So again, water always vaporizes a little bit. So even if you had a beaker of water or a glass of water, water vaporizes it. The higher temperature, the more water vapor is going to be produced, and the higher the water vapor pressure. So again, this is stuff that you just look up in a table. Let's take a look at the reaction. So in the Alka-Seltzer, it's the sodium bicarbonate that reacts. That's going to react with the hydrochloric acid. We form sodium chloride, water, and carbon dioxide gas. In this case, we want to figure out how much carbon dioxide gas gets produced. So with gases, you can't see them, you can't feel them. Sometimes you can smell them. But we're going to get the amount of carbon dioxide gas by water displacement. So if you watch that reaction, when carbon dioxide gas gets displaced or gets produced, it's going to knock off a certain amount of water. So that's by water displacement. And so when I did it, I'm going to end up with, in this case, 91.1 milliliters of water. So that volume of water produced, that's equal to my volume of carbon dioxide gas. So we actually ran this reaction early on in the semester. But in this case, we're going to get it by the standpoint of carbon dioxide gas. So when I ran that reaction, I produced 91.1 milliliters of water. That's equal to the volume of carbon dioxide gas for this reaction. So let's take a look. We're going to use the ideal gas law for this. And again, this is for carbon dioxide gas because it's only gas that gets produced. So a few things. We're going to figure out the pressure of carbon dioxide gas in a second. So we'll figure that out in a second. The volume of carbon dioxide gas, remember, that's equal to the volume of water. That's 91.1 milliliters. We got to convert it to liters, and we'll talk about why that in a second. But always convert. Whenever we use ideal gas law, convert milliliters to liters. We just divide it by 1,000 or move the decimal over 3 places to the left. Either way is the same. We're going to solve for moles of carbon dioxide gas. So this is what we're going to solve for. Our temperature is 295 Kelvin, because that's the temperature in which the reaction occurred. And then this is our gas law constant, 0.0821 liters atmospheres per mole Kelvin. So since the volume is in liters here, or the constant is in liters, we have to convert our volume to liters. Also notice that the pressure has to be in atmospheres. So we're going to convert our pressure into atmospheres and then mole Kelvin. So again, temperature has always got to be in Kelvin for these gas laws. To get the pressure of carbon dioxide gas, we've got to do a little bit of algebra. And so the way we're going to do this is the atmospheric pressure. When I did that reaction, basically PATM, the atmospheric pressure, is equal to the pressure of carbon dioxide gas, which is going to be most of the pressure, plus a little bit of water vapor pressure. So we have to take that into account. I'm just going to rearrange this equation, solve for pressure of carbon dioxide gas. So pressure of carbon dioxide gas then, so I can go to here, is atmospheric pressure minus a little bit of pressure due to water. The water vapor pressure. So let me go ahead Plug this in. So 767.5 millimeters of mercury minus 19.8 millimeters of mercury. So when I do that, the pressure of carbon dioxide gas then, that's equal to 744.7 millimeters of mercury. So a couple of things. If you look at the ideal gas law constant, the pressure has to be in atmospheres. So we'll convert to atmospheres. So basically 760 millimeters of mercury is equal to 1 atmosphere. So basically you divide millimeters of mercury divided by 760. And so when I do that, I'm going to get 0.9838 atmospheres of pressure. So I went ahead, again, we're going to go to the ideal gas law, and we want to solve for N, because that's my moles of carbon dioxide gas. So I rearrange the equation, so PV over RT, plug everything in, so I have my atmospheric pressure, my volume of carbon dioxide gas, the ideal gas law constant, and then the temperature. Again, temperature is just room temperature. So when I do that, notice that atmospheres cancel out, kelvins cancel out, liters cancel out, and I'm left with moles. Again, moles are going to flip over to the top when I do that. So this is my moles of carbon dioxide gas. Now this is equal to my moles of sodium bicarbonate. So again, we're looking at moles of sodium bicarbonate. And the reason is a stoichiometry. 1 mole of sodium bicarbonate reacts with 1 mole of hydrochloric acid, forms 1 mole of sodium chloride, forms 1 mole of water, forms 1 mole of carbon dioxide gas. So they're equal to the same. So that's equal to moles of sodium bicarbonate. So moles of carbon dioxide gas produced is equal to moles of sodium bicarbonate by that 1-to-1 ratio. So basically what we're trying to do is, I weighed that Alka-Seltzer, you watched that in that video, I weighed that about 0.609 grams. And what I'm trying to figure out is, well, what's that percent of sodium bicarbonate of that Alka-Seltzer? Again, Alka-Seltzer has like aspirin, wherever it has in there, but it has some of it is sodium bicarbonate. That's the percent we want to figure out. We want to figure out the percent of sodium bicarbonate out of this 0.609 grams of Alka-Seltzer. The reason we like percent, it doesn't make a difference at how much Alka-Seltzer I weighed out. If I weighed out 10 grams, 0.1 gram, the percent of sodium bicarbonate is going to be consistent. So I got my moles of sodium bicarbonate. Remember, that was equal to the moles of carbon dioxide gas. Well, to go from moles to grams, we just use the molar mass like we always do. And so 1 mole of sodium bicarbonate is 84.01 grams of sodium bicarbonate. I worked this out. I'm going to end up with, I think I got it here, 0.311 grams of sodium carbonate. So basically, out of this 0.609 grams of Alka-Seltzer, 0.311 grams of that is sodium bicarbonate. To figure out the percent, to finish it off now, well, I take the grams of sodium bicarbonate divided by the grams of Alka-Seltzer, so that's the total grams, and then times 100. And when you do that, I got about 51.1%. So in Alka-Seltzer, about 51.1% of that is due to sodium bicarbonate. Again, the rest will be aspirin, etc.